quantum Hall fluid that's a disk, and we argue that on the boundary of the disk there are modes that run around in one direction, they're chiral modes. And we derive the action of these chiral modes. It's a slightly weird looking action. The action for these modes. So M is the thing that's been following us through all these lectures. It was the M in a Lockheed wave function. So it's the filling fraction, 1 over M. It was the level of the Chern-Simons theory, and now finally we see that it's the thing that sits in front of this action. So it's always an integer. And these live just on the boundary. Boundary of this disk. And the action was T5, X5. If we were on a disk, I tend to call this sigma not the periodic coordinate. So it's V sigma 5. So this was a slightly odd action. We argued that this is in fact an action for a chiral mode. Suppose that when it goes one way or the other way. Phi was periodic. And this action describes various things. So this is what the disk looks like. And if you were to just look at small fluctuations of phi, they wouldn't carry any electric charge. Okay, the small fluctuations. And they correspond to sort of, sure, they're basically area preserving ripples. So it goes in somewhere, it has to go out somewhere else. And they're ripples that just move around in a chiral fashion at this speed. So they're the fluctuations of phi.
So the fact that they are area preserving, that is
no, I didn't mention that. I mean, physically it's because this is an incompressible fluid. Mathematically, I'm going to be out of my depth very quickly. Algebra of area preserving things is a W infinity algebra, which is the same thing as a all of these things are tied together somehow in some algebraic world. But I think it's interesting. But then there were the slightly more interesting excitations. So classically, the interesting excitations were where phi winds some number of times as you move around the circle. These were the classical solutions that carry electric charge. And so quantum mechanically, the way you write down operators that do that is the electron operator. So there's a non-ordering issue. I and phi. And the fuzzy hole operator. It's just e to the I. So this is kind of the smallest thing you can write down because phi is periodic. So you want to write an operator which is single valued. So this is the fuzzy hole, this is cylinder.
So V, which is right now floating around,
yes,
doesn't get into any of, because this is related to the winding. So V doesn't come into the picture in terms of any electron correlations or
no. So that's right. All the statements in terms of operators will be independent of V. The only exception is the Hamiltonian, which covers a V in. Okay, so what we're going to look at in this lecture is a few more aspects of these quantum. Any questions about this? So I want to do two things. Both of them I think are lovely. One is a really nice experimental prediction, and the other one is a sort of miraculous theoretical statement. So we're going to look at propagators. And it's going to be a little bit unsatisfactory. You know, ideally what I would do is I would start with this action and I would just derive the propagator from this action. And you can do it, and I did find it somewhere in the literature eventually, and it's remarkable thing, which is this action. So let me just tell you the result, because the result is very easy to believe. And then I'll tell you sort of how you can think about it without doing all this. So this is fiddly using this thing that I call the Florian-Jacob action. although you can do it. It's tricky because there's some horrible contour into it. Okay, but the answer is the following. So the answer is phi into x and b and c. By 0, this is the propagator, as usual, there's some basic time ordering variance. Minus 1 over m log x plus beta. Okay, plus constant stuff which in fact, the log should be something dimensionless, so there should be a UV cutoff that's in there to soak up the dimensions, which again I'll just
why did it this specific argument for
Only x plus b divided.
because it's chiral, because phi only depends on x plus beta. It's a chiral when it only goes one way. Let me say it differently. That's also a true statement. And now on the right hand side you can see that. Okay, why should you believe this even though I haven't done the calculation? Here's a very simple calculation. By the way, how many of you have done string theory 101? Okay, so you're at a huge advantage here. It's maybe the one time where string theory really helps in the matter. Because you've done all these calculations. Okay, this is Virasoro-Shapiro, Veneziano. This is sort of basic string scattering. Every one of those calculations is going to be. Okay, so why should you believe this? Suppose you were to take just a massless scalar field in one of those calculations. Usual action, no funny business. Phi dot squared minus phi prime squared. Okay, with no mass term. Very, very easy to compute the propagator for that. What do you find? You find that it has this term, log of x plus beta, plus log of x minus beta. Okay. Why does it have two terms? Because it's a scalar field, and some of it can go that way, and some of it can go that way. They're the only two options for a massive scale. So now we've basically got half of that. The whole point of this action is that it was a funny action designed to give you a chiral field, which only moves in one dimension. So it shouldn't be that surprising that it's just that chiral half. The 1 over m, of course, is easy to see. That comes from that SNM.
So David, if I think of doing the log determinant of this derivative operator here, so that looks like that this is log determinant of del sigma. There's a finite bit which probably takes into account the 0 mode of phi. And then there is a log determinant of del t minus v del sigma. So del t minus v del sigma is like the So of course these are all funny manipulations, but it sort of takes into account only the 0 mode part of this stuff, and then the del t minus v del sigma, the determinant of
this
that
minus this is precisely
yeah.
And then you have to worry about this.
Yeah. So deciding that determinant, of course, is tricky. Because with the other guy, del t plus v del sigma, it makes sense. That's a standard platonic thing. So then somehow it's just square root of that determinant. It's the same problem as in the case of the Faffians of the Freudians. Because you're trying to do a square root of the determinant, but somehow it works.
As a scalar field, the canonical kinetic energy term, but on a slightly funny metric, because it's got a light cone GT sigma and G sigma sigma.
So it's metric G is 0, half.
Right, and then some ones. And the determinant is fine.
It's true.
And so then, okay, it's slightly funny. Now, in 2 dimensions, you can always go to conformal gauge. Blah, blah, blah. And then, standard problem. I'm just wondering.
So what? In that way of seeing it,
Yeah, how does the word...
how do we get just the chiral part? Now we've lost the unit.
But this sheet has determinant minus.
It's probably what it should be, in space-time. I don't know. Normally, flat space can be written as
Okay, so the thing we really want to compute isn't the propagator for this guy, it's the propagator for this guy. And again, if you've done string theory, you've done this calculation forwards and backwards, starting from this, deriving this. Let me want the electron propagator. Which I'm going to call GF x of t, which is defined to be sin lambda psi 0. Okay, so how do you do it? One possibility is you open up your string theory notes. You can have my string theory notes if you like. It's all got there in glorious detail. Alternatively, just go back to first principles. It's Wick's theorem that we're really using here. Wick's theorem, these kind of operators. You can even just go back to think about the harmonic oscillator and convince yourselves of the harmonic oscillator, how this works. If you want a very quick three-line argument using the harmonic oscillator, I put that in the quantum field theory. Quantum Hall printed notes. So I'll just tell you the answer here, and then if you want some explanation. This is what you get by any of those methods. People have to do this. Some clarification. So what does this mean? We've got this. You've got so obviously this is written in terms of the correlator of phi. You've got the correlator of phi above. So the upshot is a very simple but very nice formula. So the propagator, here I've written it as x and t, but you can see on the right-hand side it manifestly just depends on the combination x plus bt, and it's given by x plus bt. Okay, all good. There's lots of lovely physics buried in this very, very simple. So let me tell you why this is interesting. The first thing to note is the usual.
The M's.
The M's work, right? There's a minus one point. This normalization is different from string theory where you just put a minus one. But again, it's related to this point I made about the CFT. If this were a CFT course, the canonical thing to do would be to rescale phi so that it had periodicity 2 pi to the square root of n. Then this becomes.
So this shows that you must have m odd, right? Because otherwise it's not unique. Because if we flip the arguments here, then you will pick up a minus sign. And
so I think this is the same thing we saw yesterday, that when m is odd, this is a fermionic operator, and when m is even, it's a boson. And so if you really want to describe a quantum Hall fluid of electrons, m has to be odd, which we've now seen from numerous perspectives. But you could well imagine that at some point in the future, or maybe already, I don't know, they've made a quantum Hall fluid bosons in some other system, in which case m is even.
so the electron behaves like that. So is my thing about the electron. You are calling this an electron.
Yes.
It's some kind of positive.
And when m is odd, and you're talking about a gallium arsenide system, to remove these little quotes is really an electron. As we're at least half a string theory audience, we can think about electrons as being whatever d0 can come in decision large. Okay. All right. So let me tell you the usual result. So the usual result for a Fermi statement that I'm telling you. Think about Fermi liquids in 1 plus 1 dimensions, or Fermi surfaces in any dimension. In 1 plus 1 dimension, this is the energy, this is the momentum. It doesn't matter whether you have relativistic fermions or non-relativistic fermions to begin with. And suppose you've got non-relativistic fermions. You fill up Fermi C, and what you have at the end of the day here are the excitations of basically a relativistic fermion that goes that way. Remember, the group velocity is the energy divided by the momentum. So this has velocity going in one direction, and this has velocity going in another direction. So in 1 plus 1 dimensions, a Fermi surface always has basically two decoupled fermions, a right mover and a left mover. And you can think about the physics just of one individually. If you do that, you find that it has this propagator with n equals 1. And if you want a little bit of extra convincing that's plausible, n equals 1 is the completely filled lambda. The completely filled lambda level is fine for the major. So it might be what you expect. By the way, this is called a not-yielding. The Luttinger liquid is the name given to the Fermi liquid. It's slightly. Here we've obviously not got the usual Luttinger liquid. So the story, or the theory, with M not equals to 1 is called the chiral Luttinger liquid. Even though its defining feature is that it's not a Luttinger liquid.
It is not Luttinger for n equals 1 either, right? It's
Yeah, in fact, the sensible thing to do would be to call n equals 1 the chiral Luttinger.
Yeah, that's what I was thinking.
But Xiaogang gave this name and said that the general case of n equals 1 should be the chiral Luttinger liquid to distinguish it from it's different. And so the key point is that it's not equal to 1. Okay, from now on, everything that we need for the next 15 minutes is going to be dimensional analysis. It's going to be dead easy. So the thing we learned from this was the two-point function of the electron. So the electron operator has dimension this is essentially a relativistic system. Right? Things aren't traveling at the speed of light, they're traveling at speed v, but nonetheless they're traveling in a way that's consistent with the Lorentz with speed v instead of speed c. So when I talk about dimensions, I get to set length and time to be the same. That means some relativistic context. And I mean a quantum theory, so quantum theory means you can set h bar equals to 1, which means you can set units of energy to be equal to inverse units of time. Okay, so when I talk about dimensions, I'm going to talk about dimensions of energy, which is the usual relativistic way to think about dimensions. So the electron operator has dimension m over 2. Why is that? Is because x has dimension minus 1, and this is two electron operators. On the right hand side we have dimension m. Okay. Instead of usual dimension, which is a half, which now you can see in two ways. I said that the usual dimension was when n equals 1, and that gives a half. If you just think about the action for a Dirac fermion, a Weil fermion in 1 plus 1 dimensions, fermion is also dimension half. So everything is. It is an experimental dimension. This is our Hall fluid. And it's going to look a little bit like a bomb. This is a wire. And this little box thing here has a fancy name in the literature. It's called a tunnel junction. And as far as I can tell, it's a bit of plastic.
Or air. Or air or any insulation.
Oh, air is fine? Okay.
Any insulation.
So the wire doesn't connect to the hall.
That's right. The point is that this is some insulating material where electrons from this can tunnel through to electrons from this. But there's a barrier to it.
If we were doing STM, this would be air.
Just the tip of
Tip, that's like air.
I see. In air is, usually in these systems, air is.
No, presumably they put some dielectric there. Small.
Is that also a fancy name for a bit of plastic?
Like silicon.
If you want to look at the other things, mica. In India, dielectric obviously means the one.
In school. Okay, so all right. What does this mean if you're a particular kind of theorist? It means that there's an action describing this coupling, and the action is there's some coupling constant now. Everything's taking place just at one point in space, so it's an action just quantum mechanics. And all it does is couple the electrons in the Hall state, which now this is evaluated at some particular point 0, which is exactly the point where contact is, with the electrons in the wire. Okay, so what does this do? It kills an electron in the Hall state and creates an electron in the wire. So it's just a coupling that allows electrons here.
This is capital side there, that's the outside.
So these are electrons on the edge. This is the electron in the wire.
So if you are inside the Hall system, you are calling anything that carries 1 week of charge as electron. It's not really an electron.
Well, you know, in the Hall system, it really is an electron. I think you have gallium arsenide, this is precisely an electron.
So tau is the tunneling amplitude.
And tau is just a coupling constant. Sorry, what I was saying earlier was really sort of my string theory genes coming to the fore. If you're a hardcore condensed matter person, this is genuinely an electron, and M is always odd. And in fact, for most people, M is equal to 3 because that's the thing we do. We do experiments 1/3. But I was just saying, in general, theoretically, there's no reason you couldn't have quantum Hall systems being made of any objects. They don't have to be electrons. I don't know if they can say.
And these operates with the odd dimension, right? They don't have dimension half. They dimension n by 2, right? So
Yes.
electrons will they have dimension half.
So this has dimension n by 2, this has dimension half. What we're going to do is understand the consequences.
So that's what I'm saying. If it's a dimension m by 2, why are we calling it exactly an electron in the first?
Because that's what it is. It's, if you ask what's it made of in terms of standard model particles, it's not. Actually, I think that's a little bit facetious what I just said. What's really going on is it's an electron in a very particular environment. And so it's certainly the object which carries all the quantum numbers of an electron. But it's certainly not an isolated electron. So what's really happening is it's what's become of the electron when you put it in this environment, which involves lots of collective effects from all the other electrons there, which in some sense address this object. So I think I take back what I said. It's not an electron itself. It's a composite object made of lots of complicated things that carries fermionic statistics of an electron and the same charge. So there's nothing to stop it, that object changing here, because the quantum numbers of these two structures.
So just to say that it wasn't clear to me either it was the electron, because the way you presented it now so beautifully is that there is an emergent gauge field with the introvert. And this is the edge excitation of that.
Yes.
And even in a system where we began with electrons, it's not so entirely clear that edge excitation is a quote-unquote standard model electron. by the end.
But it's made of electrons.
It's made of electrons. It's some collective state made of electrons.
I think that's it has the same quantum.
Yeah. And you spin, we haven't talked about this.
No, that's right. So everything here is in these experimental systems is spin polarized just by seeing the splitting. So all the spins are pointing up, and presumably here spins can be up and down, but it's only the ones that spin up that will tunnel through. That would be my guess. All right. So what's the physics of this? The dimension of the electron operator in the whole state is equal to, and the dimension of the electron operator in the wire is just normal. Even this isn't a standard harmonic. This is only a wire, and it's got all these excitations around it. You can be dressed by everything's messy.
Okay, but it's more of a conventional electron.
Yeah, okay.
Wire. It's some Fermi liquid, weakly interactive.
That's right. It didn't get screwed up quite as much as this guy.
Yeah.
Okay, so what does this mean? Let's do some dimensional analysis. And what we're going to get to is that the dimension of tau is 1 minus n. Okay, so why is this? The action is dimensionless. This has dimension m over 2. This has dimension 1/2, so the whole thing has dimension 1 plus m over 2. This has dimension minus 1, so this has dimension m minus 1 over 2. Good. And this has to exactly cancel with the negative. So that's the dimension of tau, to ensure that the action is dimensionless. And so let's ask a simple question. What's Ohm's law? Alright, so we all know what Ohm's law is, right? Ohm's law is V equals I. So let's see what happens here. Ohm's law relates the current to the voltage. Okay? The current is number of particles per unit time. So number of particles is dimension, it's only per unit time. And it's 1 over time is dimension. The voltage is actually an energy. The energy is E times V. So this also has dimension 1. But the current across here comes from this matrix element. The matrix element of quantum mechanics is coming from this part of the Hamilton. Yes.
So why do these have dimension 1?
Yeah, this is number of particles per unit time.
Per unit time.
So that's 1. V is the same thing.
Per unit time doesn't that come with some conditions?
No, time is the same thing as inverse energy because h bar is 1.
You mean the mass dimension of it?
Yes.
Mass dimension.
So this is with h bar.
Sorry.
This needs h bar to be 1, so we can talk about dimensions in the same way we do right.
Okay.
And I'll also set V equals to 1, but I'm not sure that's necessary.
So the current is number per unit length. Is that what you're saying?
No, number of particles per unit time.
Per unit
So
time.
it's in dimensions of 1 over time.
Mass dimension.
Mass dimension 1. That's what you.
Yeah, all these dimensions
Oh,
are
I'm sorry. I'm sorry. I thought that meant trivial. I got all confused. Okay. This means mass dimension 1.
Mass dimension is a bad word here.
Yeah, it's okay. I got it. And voltage, which is just energy.
Just energy. All right. However, the current is only moves from here to here. It comes from this matrix. So it has to be proportional to tau. And in fact, if you think about basic undergraduate quantum mechanics, the relevant thing here is Fermi's law. So Fermi's law of rules tells you the transition from one state to another per unit time, and it's basically sort of mod squared of the matrix. Okay, it's just propagating. Which means that this current has to go to the outside. Okay, Fermi's law. All right, how can this work? This has dimension 1. Tau squared has dimension 1 minus m, which means that for the dimensions to work out, there's nothing else in the game. In particular, if temperature is 0, so we don't get to play around with temperature. This has to be V. Just one dimension.
across the tunnel.
By the way, there's one thing I should have just said here. This is the dimension of tau, so this is an irrelevant operator, which I'll use slightly bad. I'll say that tau itself is irrelevant. When n, that means that we can trust this. We can do this kind of perturbative analysis if we're at low energies. Where low energies now means the sequence. So it's a trustworthy calculation if you're at very small temperature, zero really. Okay, so it's a striking result because it disagrees with what we know about in nearly all other materials. What we learned about in class. V is not equal to IR. V is equal to I to the power 1 in this system. Alright, so I did manage to dig out some experimental data that looked at this for the quantum Hall state U equals a third, and they find that I is equal to V, and the experimentally measured value here is 2.7. I don't know enough about experiments to know if that's good or bad. I do know that 2.7 is closer to 3 than it is to 1, so it looks pretty good to me. But, what the error bars were, why it's 2.7 or 3, but it's clear that in these systems, Ohm's law is violated. You get I equals V2.
So wasn't there a similar rule in vacuum tubes? Like there was in vacuum tubes there was an non-trivial exponent. Like it wasn't the usual.
Is that true? I don't know. So vacuum tubes means current in vacuum.
As in the old vacuum tubes, like the rectifiers, like the pre-transistor.
I'm sorry if I come across as I was around as well. So just, I had a sort of similar thought, which is, what would be the case that this is a tunnel? What's really going on here is that the electron will tunnel, as we said, through this whatever dimension, and the voltage will enter in the tunneling process, right? So then, you might expect the current actually to go exponentially or something.
To the minus V. Is that what happens in? These can't be quantum effects. These are all vacuum tubes.
I don't know, but it gets. I didn't mean the vacuum so much, but I just mean in this case, the fact that it's power itself isn't entirely clear to me.
Why? You're thinking like this.
Think of quantum tunneling. You're not going across the barrier that it will be an exponential.
No, but quantum tunneling, if you have a potential maybe I'm thinking of a barrier, but it's actually not a barrier.
Maybe it's the tau is the thing that would be your e to the minus.
Yeah.
So wouldn't tau be dependent on the voltage? That's what I mean. So why does the voltage affect the current? This is the voltage across the junction.
Across the junction, you need states on this tunnel. So usually, if you just have two metals separated by this, you basically talk about that there's one Fermi energy. Since you have kept this at a higher voltage, the Fermi energy is higher, and then the electrons can tunnel because they need available states to tunnel. And hence it depends on, let's say, the voltage difference that I keep between these two states. So the insulator only gives you a matrix element. It doesn't tell you how the voltage. So the barrier of the insulator is not the V. No. The V is just how much I'm changing levels here and there.
It's not as if you change the level, but you still have just a few states above the Fermi surface you can go to. Some of the number of states available scales with you.
In this case. In the usual case, it would be V because then you're right, then the Fermi level is only changed by order V, assuming V is small. And the number of states that you could have gotten is some density of states times whatever.
Yeah.
And that would have given you something like a Ohm's law, essentially.
But you're saying the quantum fluid, sort of Hall fluid, there the number of available states changes more. This V is presumably being, in a sense, is changing the number of states of the quantum.
One way is
It's changing the density of states.
Available states, that's what I think.
So say available states is because you're changing the Fermi level.
Yes.
So you're changing whether things are occupied or unoccupied. And when things want to tunnel, the things, the Fermi also thinks there has to be unoccupied.
But it's not changing the density of states. It's based
Not-
on G at EF.
That's why I
and
said
then multiplied
N2
by-
times V.
Yeah,
That's what I said. It's not density of states.
Change the number of states, but not density.
Number of states, but not density.
And on the left hand side,
How do you change the integration?
just because you have more states.
So
So you see, one of them is higher.
one of them is higher.
So it can go all the way up.
Yeah. See, actually both is happening, and it's basically your usual Boltzmann-like thing
But
that
now it's going out, right, to the wire region, right? So doesn't that care about how the total number of states in the wire as you change?
But that's just some G number of states. Is whatever the density is of the Fermi surface. And that acts times B.
So that can't give us.
that would be not V to the power.
So
That's the usual Ohm's law that I was telling you where the V comes in.
You want a more complicated argument to see.
I think it has to do with.
wondering.
I think it has to do with.
I thought it was the
quantum
tunneling, but you said that's not affected.
No, not for V to the power n. But if you think of the quantum fluid, your actual excitations are like quasi-particles and quasi-holes. The electrons are not good excitations. So outside in the wire, the electrons are good excitation. Electron wants to tunnel in, it has to somehow, basically you're giving 3 quasi-holes or something like that. I think that's where the factor of 3 comes in.
Well, one way of saying this is Fermi surface picture that you really have in your mind.
That is wrong for the
only true
quantum.
for non-interactive electrons. These are certainly not non-interactive electrons, they're fusion numbers of each. So that heuristic picture, even thinking about density of states, is a non-interactive three-particle.
One way to think is probably that you have quasi-particles or quasi-holes in the quantum fluid. But when they have to get into the wire, 3 of them have to combine and then form the electron and then you get into the wire. Because in the wire, quasi-particles and quasi-holes have not been. I think that's where the 3 comes from.
That's not interesting. All right, that's the end of my attempt to do experiments. Yes.
I don't understand why should tau itself not depend on V. I would guess that the transition amplitude change would be different if the potential, the separation is different between the wire and the all state.
So I think the picture we've come to is that there's a barrier from moving to here,
Yes.
which where tunneling across this barrier can be exponentially small, just by usual instrumental. But that exponential suppression is buried inside the thing like 10. Okay. Now, what's V doing? V is just is changing the height of the states here and giving you states to tunnel into. If V was 0, there'd be no reason for a particle to tunnel from here to here because there's no energetic gain. So V is just sort of encouraging the particles to
Small question. You're saying that the current is like the transition from initial state to the final state, right? You are using Fermi's golden rule.
Yeah.
That means that's proportional to tau square.
Yes.
I guess we're confused a little bit like why the V should, if we just use Fermi's golden rule, except that you have to match the direction. Something like that.
There is a density of states summation in Fermi's golden rule for gating. It's a fermion. It has to get something. The Fermi, there will be a current from this side to that side in general, and that side to this side. This will be proportional to whatever Fermi function times 1 minus Fermi function, and that would be the Fermi function on the other side times 1 minus Fermi function, and you will take the difference to get the net current. That's where the V and the dependence on V would come in. I'm just talking normal metal.
normal methods. In this case, you don't have a Fermi function on one side, not on the other.
Not on
The whole side is very
complicated.
This question is third order, whatever. V cube being that insertion of, if I think of V as some external, you just electrostatic field. So there's an insertion of A naught in the vertex.
Yeah.
And it seems like A naught, A naught, A naught. This is some
Just
third
working diagrams. I've not seen a diagram that's derivation. I should say that this is the zero order thing you can say. There was a huge theory worked out by Kane, Fisher, maybe Hutchinson. Yeah, certainly Kane and Fisher.
Which of the famous Fisher?
This is Mac. This is Charles Kane, pre-college Hutchinson. All right, let's move on to some theory. So, last thing I'm going to tell you about these lectures is what's called the bulk boundary correspondence. First pointed out in the late 1980s by Greg Moore and Nick Reed. We saw earlier something called the Moore-Reed wave function, which was the wave function for one abelian quantum states. The way they got to that wave function was not by thinking about what electrons were doing, but by what about it. All right, so the idea is we're going to look at the boundary theory. But we'll learn not in Lorentzian signature, because we happen to, but we'll wig rotate to Euclidean signature. So in Euclidean space. So what do we have? We had our whole fluid being a disk. So this is time, and this is sigma. Then in Euclidean space, we can parameterize the boundary of this cylinder, which is where the H-mirrors live, by a convex coordinate W, which is 2 pi sigma L plus I times 2. Of course, W bar is the same thing, but with minus I times 2. So W and W bar parameterize the cylinder. In what follows, it's going to be more useful to think about coordinates that parameterize a plane. And so the way we do this,
What is it?
L was the length, the circumference of this cylinder. We had it in the last lecture when we talked about fluid. So the sigma, which is 0. And so we're going to map to the plane. And the way you map to the plane, so here the real part only takes values between 0 and 2 pi, so you can just write the exponential of W with I minus IW, so that this has e to the I, this bit, which then of course is C bar. And if you think about what this does, it maps the cylinder to the plane such that these circles here at constant time become concentric circles around the area. And in particular, the point at time equals minus infinity gets mapped to the origin here, and then as you go up, you're going out to concentric circles. And if you've done a little bit of conformal field theory, it's very familiar. This is what you use to prove the state operator. All right. Then the propagator is just what it was before. Now, it's a log of z minus w. The fact that everything was chiral, was left moving in the CFT, translates to the fact that everything is holomorphic in Z and W when you write down correlation functions. So we're going to look at correlation functions.
So if you want to detail this, I mean, because it was log of x plus
Probably, yeah. We said B equals to I think I probably So the correlation functions we're going to look at, again, are the type that we're always looking at in string theory. By the way, in formal field theory language, these things are called vertex operators, and they're usually the same language in C in string theory. So it's correlation functions of this type. You guys okay? Let me see. You sure? And this kind of correlation function follows from exactly the same kind of procedure that I used when using the two-point function for the electron data. And the general expression is exponential of minus the sum I less than j, mi and j, y, zi, y and zj. And for now, I've just picked different m's here. Well, m is maybe bad, but m1 is an integer. Sorry, all mi's are integers. I can take it to be 1, I can take it, nothing to do with the m that I used before.
Yeah, everything is less than it.
We're going to, let's say it can be anything you like. We'll see what we do for it, and we're going to take a specific action. Plugging in the value for this tells us that this very high point correlation function, n points in general, just to point out where we go, this starts to look very similar to the Lofgren function. In particular, I get my minus.
Minus should go away.
Minus goes away, sorry. Yeah, there's a minus there that comes from the i's, and then the minus there, so the minus goes away. In particular, if I take all these m1 through mn to be equal to m, then I get an m squared over m, and this really starts to look like a Lofgren function. There's a problem here, however, which is that this formula is incorrect. So there's a subtlety. And it's a subtlety to do with something that I've been neglecting so far, which is to do with the zero mode files. It's kind of annoying. But let me just convince you very quickly this formula is incorrect. The original theory, which you can see in the action or anywhere, is invariant under phi goes to phi plus a constant. If phi was a periodic field, but it didn't matter what value it took. But this correlator here, if phi goes to phi plus a constant, picks up a phase which is e to the I, the sum of all the n's times that constant. So if the theory is going to be invariant, this thing on the left-hand side has to vanish unless the sum of all those n's is 0. Because it wouldn't be invariant under that side. So the theory is invariant under phi goes to phi plus a constant, which means that the correlation function vanishes. Let me say should vanish. sum of the i's. Again, if you've taken a course in string theory, this is something that's very familiar. This is the way you get space-time momentum conservation in string theory. All the m's here in string theory are the momentum of the string vertex operators. All correlation functions should have a delta power 26 of some space time. That's basic analysis. So I'm not going to. This should convince you it must be true. To derive it takes a little bit of care. Again, if you want to see how to do it, it's done in some detail in the string theory lectures, many other string theory lectures. So the trick is, we're going to look at the following correlation. G, Zi, Zi. So we're going to put in a whole bunch of electron operators, where each electron operator is this with the m's equal, mi equal to n. But then we're going to soak up, the sum of all the m's is then m times n, the number of insertions. So we need to soak that up with something. When we soak that up, it goes called a background charge. And we'll spend some time thinking about what this background charge is. So this is called background charge. And the role of this thing here is going to be just to cancel off all the e to the I m's from these so that the whole thing makes sense. Alright, so let's see how that works. We're going to choose. So rho 0 is just something which should be there on dimensional grounds. And we're going to pick it to be this. It's going to be a choice that makes things work out nicely. If you want some justification, go back about 20 hours in these lectures where we were talking about the plasma analogy in the Loughlin wave function. The density of plasma in the plasma analogy is equal to this. Alright, so now we require I should say what gamma is. So gamma is going to be a disk of radius r, where all the points Zi lie within this disk. Sandy, should we quickly
So you introduce the background charge, I guess.
Yeah, so the normal correlation function vanishes because of what we call space-time momentum conservation. We need something to cancel that. So we're going to put an endpoint function of electron vertex operators. Each of them has charge m. We need something to cancel it, so we're just thinking about this. Okay, so it's a finite region, gamma. We're going to integrate it. It's a disk of radius r, such that all the insertion points lie inside the disk. And this charge neutrality statement, the sum of the masses is 0, turns into the statement that the n ends, which are the charges you get from these n insertions, precisely equal to the charge you get here. And the charge you get here is pi r squared rho 0, which is the area of the disk times that charge. So it's a little bit odd. We haven't cancelled it with a single object which is minus mn. We cancel it with this sort of continuous smeared charge to cancel the m's that are here, individual versions.
Gamma is the full region here.
Yeah, gamma is by definition this disk.
So you just added the 0, basically. I mean, this is the contribution just to the 0 mode.
That's right. Yeah. think that's true. It's certainly the zero mode that gives you this constraint.
So the rest of the correlator will change.
No, the correlator will change.
How will it change?
We'll see. So this tells us that the radius r is square root of 2fn b. For what it's worth, if you go back to the Lofting wave function, finite number of particles, capital N, the Lofting wave function has a size. The size of that Lofting wave function is precisely this r.
So maybe here the size, the disk is determined by how much these insertions are spread out. So I mean it's a little bit arbitrary in the sense that I could take a disk which is just about encloses everybody, or it goes a little bit further up and
yeah, well, there's actually going to be some terms we drop that are order zi over r. So it's best to have r much bigger than all the insertions.
R is not the total volume multiplied by the
Well, so far there's no Hall through, right? We've just got some operators that we're inserting that have some points, and there's a row 0 which I've chosen arbitrarily to be this, but it turns out to be the sensible choice. And then R is then fixed. But I'm going to add the extra constraint that the correlation functions I look at, all the z's are within this R. And what's more, they're well within this R. I don't really want to go too much. Okay. So if I do that, what do I get? I get that Z, I, and R.
Once you fix row 0, you don't have a choice for how big R is, right? It's whatever you want.
It is, but I'm then going to insist that the insertion points of the operators are smaller. So it's given by, well, there's the calculation we did before, Zi minus Zj to the power n. That comes from all of these guys. But then there's an extra contribution when you contract this with this. And the extra contribution is exponential minus 0 times the sum of I plus n. Which will be gamma z prime log z prime minus zi. Okay, just the same calculation we did to get this, but now it's still lying in the exponent. So we have this integral here too. And this integral here is a little bit subtle because z is complex. And so this integral is going to have two parts. There will be an imaginary part and a real part. The imaginary part, it turns out, is not well defined. Okay, it basically has a singularity at every point. Z prime. So the imaginary part is not defined. But it sits in an exponential, so we're just going to say that the imaginary part gives rise to some overall phase of this correlation function. It turns out you can actually get rid of this imaginary part by doing a very, very singular gauge transformation. You can set it to 0, but we're just going to go to ignore it. So we'll give the phase, so we just ignore it. Just give the phase. Meanwhile, the real part is something we can do. And do it, what we end up with minus J and Zj n e to the minus the sum of I squared by 4. And I should confess that when you do this integral, there's a whole slew of terms. The leading one is this, and then there's other terms which are order Zi divided by R, and I'm going to drop those other terms. Okay, so that's where this comes in there. Well within this.
This is a little different from, I mean, if you were literally to, normally if you're computing on the sphere or something, but if the charge doesn't matter, you have some background charge that you have to You could add it just for the zero mode, you know. You could literally do the path integral on the sphere, your YLMs, and just add it from zero. And then it only changes the overall momentum of the motion. So this is some other way to do it. I have to absorb. It changes the non-zero mode part too, right?
I know another way of doing it, which is the.
Sorry, Captain.
So what I'm saying is that log comes with a cutoff, in the cutoff. So, right, so you have log of C minus W divided by, let's say, LB. Then these come from the self-energy. This comes from the self-contractions of all these e to the power I phi guys.
With the background charge.
No, now, well, the background charge just takes care of the zero mode integral. It gives you the delta function there. That's one way of.
This is coming from the background. These phi's interacting with the background charge.
Yeah, that's the way you're thinking.
There's one comment, so I don't point out conformal field theory. One comment is that this is a dimensional parameter. So this is not a marginal operator. Is that related? Usually you try out a marginal operator. I've put in a specific choice of background dimensional parameter, which is a peer. Okay, but this is something we've seen. So this is the Lofton range. Which bit?
Would we have taken the room up to the end?
Yeah, and then you would have changed what we call LB. So we had to put in by hand into the conformal field here the statement of what the magnetic length is in the bottom because the CFT doesn't know. Otherwise, I don't think. Okay, so what just happened here? What we found was that the correlation functions of the boundary theory equal wave function Okay, so we've gone through this long journey, and suddenly we come back to exactly where we started. We started by guessing wave functions for electrons that gave rise to quantum Wolf fluids. We then tried to think of effective theories that captured the same physics. We then look at the boundary, and then we see that actually the boundary knows about the wave function we started with. Knows about what's happening. Let me say a few words on this. Firstly, I think this is magical. I don't really have a good intuition for why this is working. But let me just say a few words and then we can discuss some of these issues. Okay, so the first thing is this magic. The next statement is that here we derive the Lofton wave function, but we know that there are lots of other wave functions that were interesting. For example, we might think about quasi-holes. We wrote down Lofton wave functions for quasi-holes. Exactly the same thing works. Compute the correlation function with a whole bunch of electron operators, and then as many quasi-hole operators as you like, and then the appropriate background charge. What you find is the analog of the Lofton wave function, but with those extra pieces which give rise to the quasi-hole. So if you compute, let me write it down. So compute psi quasi-hole in the correlation function. It will give you the Lofton quasi-hole wave function. by the way, if you remember, the quasi-Hall wave functions were easy to write down. The quasi-particle wave functions were somewhat harder. They had a derivative in them. And in the last 2 years or so, people have figured out how to have quasi-particle wave functions in this language. And I don't know the full details, but it's something to do with inserting descendant operators rather than primary operators to the correlation. But they've now understood there's a map between correlation functions in the boundary and the quasi-particle excitations. And finally, and most importantly, this is a general statement. Meaning this is a general statement. That the correlation function in CFT is equal to all wave function. And what's important about this is it allowed you to sort of start from the beginning thinking about the quantum Hall factor. And this is what happened from 1989 onwards. Before then, people were very much trying to think wave functions that will describe interesting quantum Halls, starting with Roth. There's a whole slew of things, many of which I didn't. But from this paper onwards, from Moore and Reed, you have a much more sophisticated technology. Now don't start to think about wave functions and how electrons are entangled. Think about CFT. So the starting point from thinking about what's the quantum Hall state should be what's the theory that was on the edge. Because once you write down the theory that was on the edge, just figure out what the electron operator is, compute the correlation function, and there's your wave function. So from 1990 onwards, I think all the interesting wave functions have been derived this way. People guessing a CFT and computing correlation functions and seeing what there are. So for example, this Moore Reed paper was so important, partly because of this, and partly because they gave the simplest next example, which is just the Ising. So you want to guess a CFT, the Ising problem in 2 dimensions, to be the simplest thing you could imagine. Write down correlation functions for the Ising one. What do you get? You get the Moore Reed state that we looked at when we talked about Moore Reed.
Using this method, can you improve on the wave function? Can you go to some direction?
In fact, this is one of my puzzles. Is that, as I was saying before, my previous statement was there's nothing special about the wave function. It's a wave function which, one, is easy to write down, and two, most importantly, happens to be in the same universality class as the real wave function for electrons with Coulomb interactions. But this calculation here says that that can't quite be right. There is something special about the wave function. Because it's the wave function that counts when you put in correlation function for primary operators. And other wave functions don't. So it really is picked out against that universality class as coming from the CFT in a way that I don't understand.
Can I ask you something? It does seem that connection is Chern-Simons theory in some way. That is, Richard had this, I never learned it, but there's a beautiful connection between CFTs and Chern-Simons theory.
There are two connections. And I think what we're seeing here are the relationship between those two connections. So I think what we're seeing here is the relationship between those two different connections. So maybe I'll say a few. Let me say a few more words about why this is really hard. So what do you have? This is our quantum Hall state. And we computed correlation functions on the boundary. So these are the correlators, the points where the correlators are. But what we've done is then map that to a wave function which lives here. Okay. So it looks like the two different theories don't even live in the same spaces. We've computed a correlation function on the boundary, and it's mapped into a wave function on this this spatial slice. But even the most basic fact that we called something z in the correlation function and something z in the wave function, they're not the same z's. One of them was here and one of them was here. And of course there was a map that I wrote down, but it doesn't get rid of the fact they're not the same z's. So I think what's going on here is what you said. It's related to Chern-Simons theory. And there's a general story due to Whittle that relates Chern-Simons theories to conformal field theories. And in fact, there's two ways in which Chern-Simons theory is related to the same conformal field. And I think it's these two ways that we've seen here. So one way is you take Chern-Simons theory and you put it on a manifold with a boundary. And on that boundary, you'll get certain edge modes of a conformal field theory. And what we've seen here is just the simplest example. You want Chern-Simons and a chiral boson. More generally, you have non-abelian Chern-Simons and some Witten model. The other way is that you take your Chern-Simons theory not on a manifold with boundary, and you just give a spatial slice, which is more like this, and the Hilbert space of the Chern-Simons theory, when you slice it, is the Hilbert space of the conformal field theory. So already in Chern-Simons theories, you can slice and dice it in two different ways and get the same conformal field theory. And I think what we're seeing here is a manifestation of that. Ultimately, it must be because Chern-Simons theory is topology. And so any way you cut it, you get the same answer because it doesn't know about it. There's no metric in it. So maybe Chern-Simons theory doesn't know about the way you cut it. Maybe that's the one way to think about it.
That part would just be, if you think of it in Euclidean space, whether you slice like that or like that, you'll get a wave function with some problems there.
That sounds plausible. So they live on different spaces, but I think ultimately that's understood by the topological nature of Chern-Simons. Here's something I'm more puzzled about. See if I can explain it. I should say my puzzle might just be me thinking incorrectly, because no one in the literature ever commented this is a weird thing. I've not read that anywhere. Everybody just states this and then nothing more. Here's my puzzle. How to say it? There's a ground state here. In the bulk. And see, maybe I'm thinking too much like alias CFT. And there's a ground state in the boundary. This is the bulk ground state. And naively, I would imagine that that they're the same, and that when I excite something in the bulk, I correspondingly excite something on the boundary. And we sort of saw that yesterday. The bulk is incompressible. If I shove an electron or a quasi-Hall in there, it sort of expands a little bit, and the boundary knows about it just for very, very simple reasons. So I'm kind of willing to believe that there's a map between excitations in the bulk and excitations in the boundary. The thing that's slightly odd is that I computed a very large endpoint correlation function in the boundary CFT. That smells to me like it should be telling me about some highly excited state in the bulk. That would be what it does in ABS CFT. And somehow it's not. It's telling me exactly what the ground state wave function is. Nothing about excited states. So I'm a bit puzzled about what.
So your insertions are at future times, future and past times. At t equal to 0, this boundary wave function does not know about those insertions that are going to come. I mean,
that's right. So maybe I should be thinking about this wave function as being much higher than all the a time that's much greater than all these insertions. I'm willing to believe that it holds then, but then it holds everywhere because it's a ground state. Actually, maybe what you're saying is a way of rephrasing my concern that these insertions should be exciting the states.
Doesn't Whittle's correspondence, the second one you said, doesn't it work like that? That is, I don't know anything about it. You take the Chern-Simons theory and you construct on some slice a wave function in whatever Hilbert space, and that comes out correctly by the correlators in the CFT, in the presumably vacuum.
It's a wave function with lots of Wilson lines.
Yeah. That's right. But you take that and you slice it. Presumably that is the state of the system for those, I don't know, Wilson lines at some instant of time. And then, well, all that doesn't the way the correspondence work is that that equals the correlation functions in the CFT in the vacuum?
That's true. So the wave function of Chern-Simons theory of Wilson lines, which is, I think, the wave function you're after, is the correlation function. But I think that's just the same statement I've stated here.
But I think from that point of view, at least, the fact that you're getting the wave function of keeping the ground state, I don't know.
I think, but isn't that just restating the mathematical truism that it doesn't work? I don't understand why. You suggested something in Bangalore a couple of months ago, which was that maybe you could think of each of these insertions, and I might be paraphrasing what you said, as you're putting an electron into the system, which
I'll just be back in a second.
So maybe you could think about putting an electron in the system which goes into the bulk, and then at some later time
straight down.
Gets absorbed, but the absorbing can happen anywhere because of the background charge. And so each of these is kind of putting electrons in, which go into the bulk and then come out again. But somehow the bulk already has a ground state of Wilson lines. The bulk is described already somehow by the Loveland wave function. These are extra things on top of the Loveland wave function, and they just sit in the same state.
So think of introducing one more electron, you say, from the end, something like that.
I'm trying to think that maybe these are excited states, but they're excited states of electrons in a quantum Hall fluid, and they just add to the quantum Hall fluid. What's there? I'm not sure.
Think of adding one more to the M, and what would you write down for?
Yeah, you just write down a Loveland state with more electrons. Maybe it's like that. What we're computing is kind of the extra wave function for the electrons on top of the already.
Regarding on this slide, the wave function was connected. In the derivation, actually, you have taken a disk where all the insertions were inside the disk, right? That also means that it's on the top of all the insertions.
So R is probably here,
yes.
right? Yeah,
yes,
exactly. So I could always take. I see. So I could certainly think
the
about
wave function was
here,
calculated on that slice.
and then there's a. You might be more comfortable mapping these to these points here. Maybe.
And each point has one Wilson loop.
Yes, there's no Wilson loops in this, right? They're probably hiding, but
No, you can think of heavy particles having Wilson letters. Electrons can be heavy particles. In the bulk theory, Stans and the Wilson loops are making the heavy particles in there.
probably, yeah.
I need to understand the earlier picture where you connected 2 points to the same Wilson.
Well, I'm not sure it's quite the right way of thinking. I was just trying to think pictorially that maybe what's happening is putting an insertion here. And I might be thinking too much like ADS-CFT, and the answer is just, this is like ADS-CFT. But in ADS-CFT, if you put an insertion on the boundary, then it does something in the bulk. So I was trying to think about putting an insertion on the boundary and that electron moving in the bulk. I don't know how it would move. It would move on a geodesics or whatever. So I find it a little mysterious.
But just to understand, suppose the conformal field theorist proved the result that the two ways of relating conformal field theory to Chern-Simons theory always gave us the same correlation.
I think it's a true statement.
Which is probably maybe proved already and true. Then at least there's a mathematical explanation.
I don't doubt the result is true.
So your point is that one looks like the time looks like the holographic detection in one thing, right? And in the other one, the radial coordinate looks like the holographic detection. Is that what you're saying? Like in the bulk wave function just sees one time slice. Okay, so it looks like that time slice has the information, and then from that point of view, t looks like the orographic direction. On the other hand, this one, in which the surface of the solid cylinder has all the insertions in it, that looks like normal orography. And right, so how come these two ways of looking at it, one in which you're taking a time slice, and in the other one you're taking a radial slice, these two things are getting real definition, right? You were saying that two different two-dimensional descriptions exist for this solid cylinder.
For Chern-Simons.
For Chern-Simons, right? But if I think of the solid cylinder and cut it at some truncated, finitely truncated solid cylinder, maybe that can be mapped to some solid S groups. And I think I'm just paraphrasing something that you said a few minutes back. That the Chern-Simons theory, it's like an equivalence between radial slicing and vertical slicing.
I mean, you have Chern-Simons theory in 3 bulk dimensions with one boundary, and then the wave function you get on that boundary sort of is a universal. I mean,
it's worth saying one more statement that I missed here. That one of the big open questions, one of the most important questions, I should say, about these quantum Hall states is when you have non-abelian anions, and you can start to shuffle them around and braid them, and you can use these kind of things to build quantum computers. People would love to know more properties of these non-abelian anions. They're very hard to derive from the wave functions, but they're much easier to derive from field theories, where it's all to do with something to do with non-trivial conformal blocks, which you take insertion points around others. Something that's been well studied in the 1980s. So nearly all the information we have about anions is derived from conformal field theory, not from the wave functions. And as far as I know, there is an open conjecture, which has never been proven, which is that there's some braiding in the conformal field theory that you get from shuffling these around, and some braiding that you get from the wave functions, which is from the very phase that we computed. And the question about whether those two things are exactly the same. And I think that remains an open problem in this whole literature. It was proven about 4 or 5 years ago in a very long paper by Nyack and friends for this case, realizing versus Marie. But in general, there's no proof of this. So there's kind of deep things in this statement that are useful, maybe even technologically useful. Quantum computers technology.
Say the statement name what has been.
So on this side, the braiding is well understood. It's in Moore and Seiberg from 1987. So you can understand how the braiding works here. And on this side, one should.
So before you, we should give David a standing ovation. He's here at the end of the lecture.
Do you know I'm finished? Yeah, I take questions on it.
You sure? I mean, just because Gautam is going to go. So. All right, guys, come on. Now,
So you get an answer from braiding here. And there's a calculation you should do here that is very hard to do, which is the very phase computation of the wave functions. And the question is, do they really agree? And to my knowledge, this has never been proven. It's been proven for Laughlin because you can just do it explicitly. It was proven for Moore-Reed just a few years ago, but in general.
Sorry to ask this question which smells of the landscape, but now, I mean, can't we then just declare, take your favorite CFT, it meets all the rules of CFT, therefore it's a possible bulk wave function?
Yeah, I think that's absolutely true. There's a few requirements.
Okay, yeah,
let me tell you. There's some requirements that I don't understand that well about mutual locality of operators. these are the main requirements actually, so I'm embarrassed if I don't know those. But one very simple physical requirement is you have a CFT, and from that there's a bunch of primary operators, and you'll pick one which you believe is the electron operator. Now, this is the electron operator. And maybe you need some background charge. I mean, sometimes you do, sometimes you don't. It depends on what the CFT is. One requirement is that if you want this to describe a quantum Hall state, this should have a unique answer. But it typically doesn't. Usually, there's a very complicated because you have to pick various branch cards, and you have to pick one. And the way this is phrased is that this has some number of conformal blocks on the right-hand side. But for the electron operator, you need something where it has a unique ground state, so there's just a single conformal block on the right-hand side. I think many CFTs, interesting CFTs with non-abelian statistics, the gradient don't have that practice. We were very excited just a few weeks ago when my student Carl was here, because we finally figured out we had these new wave functions that nobody had discovered before. And we figured out they were wave functions for Western-Witten models. And there's one operator in a Western-Witten model which has this property. So we're very excited, and we wrote a paper, we're going to put it on the condensed matter archive, and then we realized this was discovered in 1990 by Shell. So we got scooped by 25 years.
But I mean, the field looks wide open. All right, let's do Witten models, but cosets.
Good. So
and then this and that.
There's states of u equals 12 fifths. These are experimentally seen states.
Yeah.
U equals 13 fifths, which are thought to be given by Reed-Redzeile states. And this is a coset model. It's SU2 at level 3, not U1. And this is the state that's most promising for building topological quantum computers. So, the idea of topological quantum computers is you take your anyons and you shuffle them around like this sweet magician, and that gives some unitary operator, which is your programming. That's your algorithm. And if you look at the theory of these guys in Station Q do, there's something called a set of universal operations from which you could do anything. You just have these operations. And this state satisfies that property. Whereas the more Reed state doesn't. It has what's called Fibonacci intervals. And for its work, these are the fusion rules which make it possible. This is a signet. So, there's a whole slew of these states where in general it's SU2 at level K, what G1. It's just that SU2 at level 3 is the one where people think they've observed what it's going. That's the problem. It's easy to write down CFTs, but it's hard to build things in the lab. I don't know if there's other, are there other quantum Hall systems where you could hope to not build them out of electrons, but build them out of something else, and maybe hope to have design of quantum Hall systems?
Quantum Hall systems out of something else? Yeah, in principle, when you can do what is called this gauge fields in cold atoms, where again the matter field interaction looks pretty much like this. Again, the issue is that those are not quite, they don't have a mu term of their own, the field, but as long as you're only looking about the atoms interacting with those, so it's like a fixed gauge potential, what you call that. But in terms of the atoms interacting with them, they look like things in a magnetic field. And then there are possibilities that you can probably make things out of it.
Something else I read is, the Lorentz force law for magnetism looks very much like the Coriolis force.
Yeah, so
B cross. So take a cold atom and just make it spin. And then you have vortices, but those vortices appear as if they're in a magnetic field. There's a nice paper by Nigel Cooper and company that suggests these can even form non-abelian quantum.
Yeah, but in most of these cases, the practical problem is that to get the kind of fields that you need to see these random levels and effects, you have to rotate it really fast. And then all sorts of things start dissipating and all sorts of... It's just practical issues. I mean, there's nothing in print.
This is important, right? 100 years, you know, somebody can spin something on
Yeah,
fast.
sure. So then what people came up with is instead of rotating, you use something like laser tracing of this field. You use some transitions, some Raman transitions. And that acts like an effective magnetic field. This is Jan Spillman in Maryland and others who've been trying to do this. In fact, Jan Spillman came from a lab which was doing quantum Hall, Eisenstein's lab, Jim Eisenstein's lab, and then he's now gone in completely into this. And one of his goals is to actually do this with quantum.
Very good. This sounds very